This is Selçuk from Milas Technical University, Günah. This is session 3 of Pvcon, and the first one will be a keynote speaker, Robbie Pepys from ISFH Germany, and his title will be Passivating Polysilicon on Oxide Contacts from Fundamental Investigations Towards Industrial Implementation. So, Robbie, floor is yours. Screen is yours. Seems like we lost Robbie. We're waiting for him to reconnect. So while we are waiting this piece of information, so this polar concept from ISFH is very similar to TopCon that is suggested by Fraunhofer ISE mostly. And in the small difference is what kind of conduction mechanism occurs through the oxide. So is it partial contacting versus a tunneling mechanism? And Robbie is very active on bringing this polo concept to the attention of people, researchers in this field. I think we can start the presentation while waiting him for the question and answer.
Hello everybody and welcome to my talk entitled Passivating Polysilicon Oxide Contacts from Fundamental Investigations Towards Industrial Implementation. My name is Robbie Pepys. I'm working at the Institute for Solar Energy Research Hamelin, and I would like to thank the organizers for inviting me and giving me the opportunity to present here our recent results. This is a big honor not only for myself but for the entire team, and many people have contributed to this work. Some of them are listed here as co-authors, and the entire ISFH team you can see here aligned in this sun-shaped pattern. Let's start with a brief motivation. You're all aware of the fact that the deployment of photovoltaics and of other renewable energy sources is important for the mitigation of the global warming effect. This aspect was quite a bit in the focus of public attention last year thanks to the Fridays for Future protests. However, as you all know, this year other topics have dominated the public perception. But it doesn't mean that climate change is locked down. As you can see it here in this left-hand picture, for example, in the extension of the Arctic sea ice. It's shown here for September 15th this year. It's the white area, and you can also see the orange line, which represents for comparison the 20 years average of the Arctic sea ice extension at this point in time of a year. And this year, the Arctic sea ice extension was the second lowest ever recorded. That means that global warming is progressing, and it also means that we have to progress with the deployment of PV. Fortunately, photovoltaics has become already the cheapest energy conversion method in many parts of the world. As you can see it here on this map showing a data collection of record low bids on tenders. And since this conference has a Middle East focus, let's look at this region here. And you are probably all aware of this record low bid in Abu Dhabi this year of only $1.35 per kilowatt hour, which is really impressive. But not only PV deployment is increasing worldwide, but also value creation via PV production is growing, and also in regions outside East Asia. For example, this map shows Europe, including Turkey, and it also indicates a couple of companies working in PV, and they are color-coded according to their position in the value chain. And as you can see here, in Turkey, vertical integrated PV manufacturers are emerging. And there are a couple of favorable circumstances for this trend. For Europe, it's the European Green Deal of the European Commission, aiming to get Europe CO2 neutral till 2050. There are also an increasing fraction of transport costs for the PV modules, and there will be a major effect of CO2 pricing in the future. In this talk, I would like to focus on the technical question whether it's possible for a new player in this field to differentiate from the mainstream via a specific cell technology. This question is actually very difficult to answer because so many different solar cell technologies exist. To assess them systematically, I suggest to focus on their junction schemes. You all know that every solar cell requires two carrier selective contacts. One is required to extract the electrons from the conduction band, and the other one is required to extract the holes from the valence band. The selectivity of these contacts is in the focus of the modern PV research since a couple of years now. And one major finding of these recent investigations is that there are much better junction schemes than conventional diffuse junctions. However, the variety of the different junction schemes and the variety of the different cell structures incorporating these junctions seems to be confusing. To get an overview, I therefore would like to try in this presentation a multi-level approach for the assessment of crystalline silicon technologies with different contact schemes. Within this multi-level approach, I would like to start from the highest flight level perspective, and that's the deduction of a selectivity limit for various electron and hole contact combinations. Afterwards, I would like to get more into detail for one specific electron and hole contact combination by numerical device simulations. I also would like to establish here the contact to the ground by representing recent experimental results for our industrial polar cells. To complete the picture, I also would like to include silicon perovskite-based tandem cells into this discussion. As a summary of this presentation, I would like to show you ISFH's cell roadmap. Regarding the definition and the quantification of the selectivity, different proposals have been made. The idea of Rolf Brendel et al. Was to define the selectivity of a contact. Let's consider here as an example this electron collecting n-type doped polysilicon and oxide contact as the ratio of resistivities for the minority carriers. Those is the carrier type which should not be collected by this contact, in this case the holes. Their resistance should be as large as possible, divided by the resistance for the majority carriers, which are in this case the electrons, and they should be collected effectively, and therefore their resistance should be as low as possible. And after doing some math, you can calculate that this definition comes down to the thermal voltage divided by the saturation current density for the recombination of minority carriers times the specific contact resistance for majority carriers. As you know, the free solar cell has two contacts, and therefore you need to calculate a combined selectivity according to this equation. And as shown by Rolf Brendel et al., this combined selectivity can be correlated to an efficiency limit which is implied exclusively by the contacts. That means the solar cell is considered otherwise as ideal. No other extrinsic losses are taken into account, no parasitic absorption in these contacts is considered, and perfect Lambertian light wrapping is assumed. Of course, this approach will yield an overestimation of the efficiency of a real device, but it nevertheless allows for a comparison of different combinations of contacts on equal footing for a given experimentally determined set of rho C and J naught data. With this approach, we screened different contact schemes, electron collecting contacts and hole collecting contacts. We include different variations, including diffused junctions, for example phosphorus diffused junctions. We also include amorphous crystalline silicon heterojunctions, polysilicon and oxide based junctions, and also metal oxide based junctions. In total, this results in a very large table, but let's focus on the most relevant cases. The industrial most relevant case is the combination of a phosphorus diffused N-type emitter with local aluminum P+ hole collecting contacts, because this combination is implied in the so-called PERC cell, which is the working horse of today's PV. For this combination, we calculated a combined selectivity of 11.7 and a resulting selectivity limit of 24.5% for the given G0 and ρC data as specified in this work. Let's briefly consider the current status of this contact combination. As already mentioned, it's implemented in the so-called PERC or PERC+ cell structure as shown here. It was proposed already in 1989, and it has been transferred to mass production in the last years. The market share today is around 70%, and it's actually increasing. The energy conversion efficiency of this cell concept has been improved almost linear with time in the last years, with a rate of around 0.5% absolute per year, and it reaches now values of slightly below 22% for the leading companies. In 2019, already efficiency values above 24% have been announced for record R&D PERC cells. It's worth to mention that a PERC cell can become bifacial by not printing the aluminum on the entire rear, but rather printing aluminum fingers. We call this concept PERC+. And by this bifaciality, you can gain an additional energy yield of around 10% on an annual average at the latitude of Germany. And of course, the benefit will be even higher in more sunny regions. All these features together make the PERC cell and this specific contact combination a very tough benchmark for any other cell concept. Nevertheless, it also has some inherent weak spots, in particular the recombination in the phosphorus doped N+ region, in the passivated regions, but also and in particular in the metallized regions, is significant and poses a certain efficiency limitation. Another very promising combination of electron and hole collecting contacts is the combination of an N-type doped amorphous silicon layer on an intrinsic layer with an P-type doped amorphous silicon layer, also on an intrinsic layer. And this combination here can reach, according to our input data, in combined selectivity of 13.2 and then a selectivity limit of 27.5%. And this combination is used, for example, in the current world record cell for crystalline silicon single junctions from Canica, which reaches an efficiency of 26.7%. So it's rather consistent to our simplified consideration. Also for this technology, let's briefly consider the current status. Also, heterojunction cells are not very new concept, but have been rather proposed already a long time before. But currently, the mass production of heterojunction cells seems to gain momentum, as you can see it here on this world map, showing different players in the heterojunction field. The current R&D record for a heterojunction cell, full area measured, is 25.1%, achieved by the company Hanachi, and the median in mass production, for example at Meyer Burger, is above 24%. This technology has nevertheless also some weak spots. In particular, the capex is higher than for PERC. Okay, let's move on to another very promising combination of electron selective contacts and hole selective contacts. In this case, consisting of a stack of a thin interfacial oxide covered with either P-type doped polysilicon for the case of hole collecting contacts, or N-type doped polysilicon for the case of electron selective contacts. These polysilicon layers may also contain other components such as carbon. For all of these combinations, we obtain very high combined selectivity values, exceeding values of 14, and the corresponding selectivity limit is also very promising. It exceeds values of 28%. This combination of contacts was actually implemented also in our 26.1% cell, which is still the record for homojunction silicon single junction cell. Also for this contact combination, let us consider the current status of the technology. Before, I would like to spend some words on the history, because I would like to acknowledge that this junction scheme originates from the bipolar junction transistor community, where it was developed already in the 1970s. It was already applied on solar cells in the 1980s with rather moderate cell efficiencies, and then it was apparently forgotten for a long time. Apparently means that companies such as SunPower may have worked on this junction scheme in the meantime, but they never disclose it. For public photovoltaics, this concept was rediscovered in 2013 from ISFH and Fraunhofer ISE together at the same conference. Meanwhile, this has become a mainstream technology, and numerous groups and companies worldwide obtain excellent results. Regarding the cell structure, for an implementation of both an polysilicon oxide junction collecting holes and polysilicon oxide junction collecting electrons, the simple cell structure you can think of as a double-side contacted cell with an unpatterned polysilicon oxide junction on the front and on the rear. In this case, the polysilicon layer has to be very thin, because otherwise you would suffer from parasitic absorption, and this thin polysilicon layer may need additional conductivity provided by a TCO. And with this cell concept, we so far achieve very fair efficiency, I would say, of 22.3%. And we found in particular the interplay of TCO and the polysilicon as much more challenging than expected. However, you can also implement an electron collecting polysilicon oxide junction and a hole collecting polysilicon oxide junction in a cell concept without TCO if you put both junctions on the rear in an IBC structure. This is actually the cell concept for which we demonstrated the 26.1% on lab scale. And we think that this is not the full efficiency potential of this cell concept and this junction combination. And the justification for this claim can be seen here, where we plot the implied pseudo-efficiencies as calculated out from injection level dependent infrared lifetime mapping measurements at different process steps. And after passivation of our cell, the implied pseudo-efficiency is much higher than the final efficiency of the cell and exceeds 27%. And the reason why we drop here is a degradation induced by the process. And we are working on its mitigation, and we hopefully can achieve higher values in the near future. Regarding mass production, one has to acknowledge that, for example, SunPower is producing similar cells with a median efficiency above 25%. And also LG is producing very similar solar cells. The weak spots of this technology, of course, are that the process complexity is significantly increased as compared to a PERC cell. Okay, let's move on with the combination of a polysilicon oxide junction with a conventional diffused junction. The most prominent cell structure, including such a combination, is the so-called Topcon cell structure, which combines a conventional diffused boron frontside emitter with a polysilicon oxide electron collecting junction on the rear. Unfortunately, we have missed the boron emitter here in the screening. Nevertheless, we think that the results for this combination are pretty much comparable to the results for the mirrored polarity case. The mirrored polarity case means the combination of a phosphorus diffused N-type frontside emitter with an P-type hole collecting polysilicon oxide junction. And for this combination, the combined selectivity is around 12 and the corresponding selectivity limit close to 25%. For such a Topcon cell, as illustrated here, industrial and the record efficiencies up to 24.8% have been announced. This is pretty much consistent with our selectivity screening. However, I also would like to acknowledge that on lab scale, even higher efficiencies up to 25.8 and 26% have been achieved. That means that some components, probably in particular the boron emitter, has better properties than we assumed for our selectivity screening. The mass production has already started at some companies, or at least pilot mass production, and the median efficiencies, as reported, for example, by the company Jollywood at the Pvcon conference this year, is in the range of 23.8%. Nevertheless, this technology also has some weak spots. In particular, the process complexity is increased as compared to the PERC cell, and also metallization costs are increased because the rear side is metallized by silver rather than by aluminum. Last but not least, let's consider the combination of an electron-collecting polysilicon oxide junction with an hole-collecting aluminum P+ junction formed by aluminum alloying. This combination has a surprisingly high combined selectivity of up to 13 and a corresponding selectivity limit exceeding 27%. And therefore we think this combination is quite interesting and worth to look at it more in detail. To get a realistic assessment of the efficiency potential of this specific combination of an electron-collecting polysilicon oxide junction and a hole-collecting P+ region, we perform numerical device simulations to include all relevant extrinsic losses. We use the Crocker-2 implementation of the conductive boundary model and combine it with a synergistic efficiency gain analysis. The optical generation profiles are calculated by the ray tracing software Sunrays by using experimental NMK data for each layer, in particular also for the polysilicon. And the input data for the numerical device simulations are listed here in this table. It's probably difficult to read them now, but I would like to refer you here to our recent publication. Briefly summarized, these input data are either measured on test structures or best literature data. So these are the best data for each quantity we can achieve or found in the literature. We also draw the assumption that the polysilicon can be metallized without harming its passivation quality, which is at least more or less true for n-type doped polysilicon. One possible cell structure comprising this combination of an electron collecting N+ polo junction with the hole collecting aluminum P+ regions is this polo back junction cell as shown here. It features aluminum fingers on the front side, just like the rear side of an PERC+ cell. The simulated efficiency potential, according to our numerical device simulations, is 24.7%. This is lower than our selectivity limit of 27% for this contact combination, and the reason for this difference is that we here include all relevant extrinsic losses. Nevertheless, this efficiency potential is quite high, and it's significantly higher than that for the PERC benchmark. On the left-hand graph, you can see the synergistic efficiency gain analysis for this cell structure, and the different color codes here of these bars represents the different nature of these loss channels. For example, the green bars here represents optical losses, or in other terms, if you would avoid the front side finger shading completely, you can achieve an efficiency gain of 0.7% absolute. There are also some blue bars representing the resistive losses and red bars representing the recombination losses. Some advantages of the cell structure is that for one polarity the metallization is made of aluminum, which is cheaper than of silver, of course, and we are currently also working on the metallization of the polysilicon on the rear also with aluminum, and then we would achieve a full aluminum cell. This would be very promising, and the process flow of this cell structure can potentially get quite lean. To establish the ground contact, I would like to show you here our recent experimental results for industrial polo back junction cells. We are working on this cell structure since almost 1 year now, and we already achieved an efficiency of 22.6% on full M2 wafers, as confirmed by ISFH Caltech. In particular, the open circuit voltage is already quite promising. It reaches values of 760 millivolt, which is the highest value reported so far for P-type wafers with aluminum P+ regions. Of course, the simulated efficiency potential is not yet fully exploited, and the major reason for this discrepancy is that the aluminum P+ regions, as shown here in this cross-section SEM image, the bright areas are the P+ regions. They are quite narrow, surprisingly narrow, and not as good as we measured on test structures. One reason might be that for the full cell we also have to find a compromise for the firing temperature for the front side and for the rear side, and therefore the BSF formation is not yet as perfect as measured on our test structures. Nevertheless, we are making good progress here, and we are confident to improve our results quite soon. Another interesting cell structure comprising this combination of electron collecting and plus polo junctions with local aluminum P+ regions for hole collection is this IBC structure shown here, which we call polo IBC cell. For this cell structure, I simulated efficiency potential according to our numerical device simulations is 25.5%, including all relevant extrinsic losses. And this is very promising. The synergistic efficiency gain analysis is shown here in the left-hand graph, and you can see that the optical losses due to finger shading have disappeared, of course, because it's an IBC cell, and the most relevant lost channels are recombination induced, and there is a gray bar here, and this corresponds to the synergy of all recombination lost channels. That means, due to the liquid bucket principle, you could achieve an even higher efficiency than the sum of all recombination losses if you succeed in suppressing all recombination losses at once. Again, the same advantages account here as for the polar back junction cell, although the cell processing is a bit more complicated than for the polar back junction cell. Nevertheless, it is still as lean as for the PERC cell. Also for this cell structure, I would like to establish the ground contact by showing our recent experimental results. We obtain 23% for an industrial processed M2 wafer, but still designated area measurement. The reason why we still not exploited yet the full efficiency potential is similar to that of the polo back junction cell, that we are still working on the improvement of the aluminum P+ regions. On the left-hand image, you can see a photograph of a rear side of a mini module made of a polo IBC cell with a multi-busbar interconnection. For an at least almost complete overview on the different cell structure and junction schemes, I think it's necessary to also include silicon perovskite tandem cells into the discussion, because the development of this technology is really impressive. You're probably all aware of the current record of 29.1% achieved by HZB, which outperforms the record for silicon single junction cells already by far. Nevertheless, I think it's fair to remark that silicon perovskite tandem cells still have a long way to go to become major and competitive with silicon single junction cells for industrialization. Nevertheless, let's assume that they are successful. The question arises whether silicon cells with passivating contacts are at that end. And our answer to this question is, of course, no, they are not at that end, but they rather form perfect bottom cells for this tandem approach. For example, in this two-terminal structure as shown here with the silicon bottom cell and the perovskite top cell, you will need an interface passivation at the interface from the silicon side here. While this interface should not only be passivating, but it should also collect one carrier type and transport it to the top cell. And in this case, those are the electrons. They should be collected and transported to the top cell, while the holes should be blocked at this interface. And this could be achieved either by a passivating contact, for example, formed with a silicon heterojunction, or by a passivating contact formed by a polysilicon and oxide junction. And in the case of the latter, the temperature stability of the junction scheme here allows you for the processing of the bottom cell to also apply the current metallization of the rear side, which links the tandem concept to the current PERC mainstream cell technology. Also, IBC cells can be combined with perovskite top cells, and this results in a very interesting tandem configuration, which is shown here. It's a so-called three-terminal tandem configuration. Such a three-terminal tandem cell has one contact on the top and two contacts on the rear. And the additional third terminal on the rear gives you the opportunity to extract surplus carriers from the bottom cell in the case that the top cell is current limiting, or it can be used to inject missing carriers into the bottom cell in the case that the bottom cell is current limiting. By this, you can achieve a monolithic design without the constraint of current matching between top and bottom cell. And this gives you a high flexibility regarding the materials for the top cell processing, but also an increased spectral robustness and an increased energy yield. Our Polo IBC and Polo Square IBC cells can pose a good platform for lean bottom cell processing. As a summary, I would like to present you ISFH's cell roadmap. This cell roadmap is a consequence of all these considerations I've presented you previously in this talk. ISFH's background is identical to the current mainstream in the crystalline silicon photovoltaics. It's in the PERC and PERC Plus technology. And for this cell, we simulated an efficiency potential of 23.7% based on our numerical device simulations. As I have reported, we are currently substituting this phosphorus-doped emitter by an electron collecting N+ polysilicon oxide junction, either in this IBC configuration or in this polo back junction configuration. For both cell structures, we obtain very high simulated efficiency potentials, and we think we are also on a good track with our experimental work. We furthermore work also on smart concepts how to implement the second polarity also as a passivating contact by substituting the aluminum P+ region with an hole collecting polysilicon and oxide junction, either in this double side contacted configuration or in the IBC configuration. For both cases, eventually we can upgrade our cells to tandem structures by combining them with perovskite top cells to either a 3-terminal tandem device or to a 2-terminal tandem device. We think that this stepwise approach offers a good compromise between risk minimization and innovation for each step. With this, I would like to thank the entire team at ISFH, our partners, academic partners and industrial partners, the funding sources, and of course you for your kind attention. I would have appreciated to meet you in person, and I hope it will be possible next year.
Thank you, Rabbi, for this very nice overview of polo studies and also introduction of aluminum on both sides of the cell or both polarity. I will have two questions myself. So one of them is, what do you think about the promise of copper in the integration? Because you talk about all aluminum devices, but do you see any prospect of introduction of copper to the process?
Yes, I think it's a very interesting approach. I think it would be very beneficial if it could be printed or deposited already in a structure manner that you don't need additional mask to it. But regarding the material costs, of course, it's as promising as aluminum. So if it's possible to screen print, for example, it would be great, yes.
Also for the band alignment perspective, I think it will be easier to passivate than aluminum, right?
Yes, I think so.
So the second one will be on the part that you didn't really discuss much of P.PSS, molybdenum oxide, lithium fluoride, or all these non-silicon compatible thought initial materials. So what do you think about this screening again the aluminum work function by using one of the exotic materials? So can it help on getting the all aluminum devices?
Yes, I have to admit that this is not my my field of my special expertise. Nevertheless, I think this is a very interesting field of research from academic point of view. There's a lot of material science you can do, and there are excellent works published here. And I think it's very promising so far. I have not seen an junction scheme which is already, let's say, as major as the polysilicon oxide contacts, but it doesn't mean that there will not be one. I know also that some companies are working on such transparent contacts, because it would be very attractive if you could deposit them without any structuring also on the front side.
Thank you, Robbie. I think I can move on to the next speaker. This next speaker, again, a keynote speaker, Veysel Ünsür from Necmettin Erbakan University in Turkey. And he'll be talking on alternative approaches for metallization of silicon solar cells. Veysel, are you there?
Yes, Dr. Yaj, I'm here.
Good to see you.
Good to see you too. How are you?
All right. I think you will start in a moment.
Yep. Hello everyone, welcome to my talk. My name is Veysel Ünsür from Necmettin Erbakan University from Turkey. I'm pleased to have the opportunity to be here. Today I will present the alternative approaches for metallization of silicon solar cells. It will be a review of state-of-the-art technology used today. Here is the outline of the presentation. First, I will give the brief introduction about solar cells and its commercial status. Then I will move on to the motivation of this talk. And finally, I will talk about the techniques that are being used today in the solar industry. So let's get started. I want to start with the question of why do we need solar cells? This graph shows the Human Development Index versus annual electricity consumption per capita for countries in the world. HDI measures the quality of life. As you see, all developed countries like US, Canada, UK are at the top of the HDI and consume up to 15,000 kilowatt-hour electricity. However, the most populated countries such as China, India, Indonesia are still behind the 4,000 kilowatt-hour mark. Keeping this in mind, the next graph shows the electricity consumption versus per capita income instead of HDI. The picture doesn't change much from the first one. Almost same countries are above $20,000 income per capita. Another point to make in this graph, when the most populated countries that are ranked at the bottom start demanding the same amount of energy like developed countries, there will be a drastic increase in the demand that we can't provide with today's means like fossil fuels. Due to the scarcity of the fossil fuel sources and more importantly, emission of carbon dioxide, we need more resources to meet the increasing demand, which leads us to solar energy. Fortunately, surprisingly actually, all the countries that are ranked at the bottom of HDI graph are at the top of insolation map. Like India and Indonesia are more than 7 kilowatt-hour per meter square a day. And this is good news. The next question is that if solar resources is big enough to power the world. And the answer is yes. These circles are proportional with real values. The sun producing 23,000 terawatt per year while the world needs only about 30 terawatt. These circles also tells us why we need to favor the solar among the other renewable, because it's much bigger resource. One might ask where we are going to put those panels. Do we have enough space for that? When we look at this map, these little squares that you see on this map would be the required lands to supply the energy demand with solar in the world. Of course, no one's suggesting to cover all the Nevada deserts to power the US, but it's a good example to visualize things. So in conclusion, utilizing the solar energy not only solve the energy problem, but also it will help solving poverty and pollution as well. So how do we utilize solar energy? One way is to use photovoltaics. Photovoltaic device is one particular embodiment of solar energy where it converts sunlight into electricity without generating any polluting byproduct. Solar cell is an optoelectronic semiconductor device in which optically the reflectance and shadowing the illumination side of the cell need to be reduced. Electrically, the recombination at the surfaces and the bulk and the internal series resistances must be low. There are different types of solar cells, such as wafer-based, thin films. There's new generation technologies like perovskites, organic and quantum dot solar cells. My focus will be on the crystalline solar cells. In crystalline solar cells, there are also different architectures to better the performance. The first one is aluminum back surface field structure that has full aluminum back contact. It has passivation on the front surface and back surface field formation on the back side because aluminum alloy with silicon during high temperatures. This structure is the most common one in the industry because of its simplicity. The second one is the passivated emulator rear cell or PERC structure that is very similar to the aluminum BSF, except the fact that there is a passivation stack layer on the back side and the back contact is local instead of full. Interdigitated back contact is the next one. The fundamental improvement of the design of IBC cell is zero metal shadowing on the front side. So the current would be maximum. And since the contacts are on the back side, series resistance can be lowered by increasing the width of the back contacts. The last is heterojunction with intrinsic thin layers. The silicon wafer is sandwiched between two intrinsic amorphous silicon thin films to maximize the open circuit voltage. The focus of this presentation will be the PERC type because it is the rising star in the PV market, predicted that it would surpass the aluminum BSF cell market share in the near future. When we look at the market share of different solar cells, or different architecture solar cells, we can see that crystalline silicon cells are exhausting and dominating the market. We simply because of its lower cost, market maturity, and its abundance. And we also see that aluminum BSF structure is the most popular architecture among others. PERC is the second emerging alternative to aluminum BSF. If we combine all the crystalline silicon technologies, the total market share is around 95%, while PERC takes up 35% of the market. These market share numbers are not coincidental. Rather, it's all about the cost and performance. What is the measure of the performance? It is the efficiency that is the product of three parameters: short circuit current, open circuit voltage, and fill factor. This means that to increase the efficiency, all the three parameters must be increased simultaneously. To increase the short circuit current, we need to reduce the front metal shadowing and increase the minority carrier lifetime. Open circuit voltage is a function of short circuit current and can be increased by improved passivation and reduced recombination. Fill factor is a function of open circuit voltage, series resistance, and shunt resistance. To achieve high fill factor, we need to reduce total series resistance and increase the shunt resistance. This chart shows that what are the losses in general for a silicon solar cell. The first three limits come from thermodynamic, and nothing can be done about it. If photons have smaller or greater energy than the band gap of a semiconductor, it will not excite any carriers. We will also lose almost 20% to maximum power because of current voltage characteristic. It means that while working with silicon, we lose 60% at the beginning. The rest of them, such as shading, reflection, recombination, resistivity, are design dependent and can be improved with different ways, such as passivation quality for recombination, different metallization pattern for shading, etc. It is amazing how we can get high efficiency from a solar cell, giving all the detrimental factors, because there are so many that we must work against. I will not go into full detail for all, but starting from silicon wafers, they are manufactured by float zone or Czochralski techniques. They can leave some defects behind, like boron oxygen, that would lead to light-induced degradation. Next, emitter formation, which impacts sheet resistance, surface concentration, and the junction itself, that affects electrical output parameters. At the bottom of the chart, metallization factors are listed. All this improvement is what is needed to achieve high efficiency, which is important to have cost-effective solar electricity. We can have the basic idea here. This diagram shows the different processing sequences for different solar cells architectures, or where we lose all those stuff that we just showed in the previous slide. We can clearly see that some cells require more processing steps. Some are more complex than the others. The decision maker here is the maximum efficiency and minimum cost. Then how does all these differences in processing flow transfer to the cost of PV? When we look at the cost breakdown, we know that material takes about 40% and scaling is about 35%. What I like to focus on the processing cost, which is around 25% of total cost. This chart shows us the cost breakdown of processing steps of a PERC type cells. As you see, metallization takes the biggest number, followed by PECVD processes and wet bench steps. Keep in mind that this is for PERC cells. Metallization part goes up to almost 50% for aluminum VSF cells. For PERC cells, it is only 35.1%. So that's why the metallization of a silicon solar cell is an important task to tackle to be able to lower the cost. Besides metallization cost, it also affects so many variables in a solar cell. Metallization has both optical and electrical impact on a solar cell. Optically, the shadowing loss can make or break the cell, depending on the grid line and busbar width. And electric-wise, the components of series resistance, like grid line and contact resistances, can be affected by the metallization. There are different ways of metallization of solar cells, such as lithography, laser grooving, plating, and printing. Lithography uses the mask and a UV light source. On the other hand, laser grooving utilizes the laser and plating at the same time. Plating itself is a chemical process that chemical waste is its biggest problem. Also, low throughput of these techniques is another big challenge to tackle. On the other hand, printing can have as high throughput as 4,000 solar cells per hour, which is a big plus, and also its simplicity is what attracts the market the most. Printing can be categorized as impact and non-impact printing, which points out if the process undergoes by touching the solar cells or not. Non-impact includes inkjet printing, aerosol printing. Even though these are promising techniques, there are no proven industrial level machines. Impact printing includes screen and stencil printing methods that are very similar to each other. Of all these, screen printing is what dominates the market. It is the most mature, best established solar cell metallization technology. The basic principle of the screen printing process is simply to use a mesh screen to produce same pattern over and over again on silicon wafers with a metal paste. During the printing, paste is first applied to the screen before the movement of squeegee. As the squeegee moves the paste across the screen, a shearing action causes a decrease in viscosity, allowing the paste to pass through the mesh openings to the desired silicon substrate. The main factors that influence the printing quality are related to screen, squeegee, and the metal paste. This figure here shows the metal paste for front-side metallization. Metal paste includes metal powder up to 85% in weight, glass fluid up to 3-4% in weight, and the rest is organic binders, solvents, and additives. Every component in the paste has a role. Metal particles provide the conductivity since they are the metal bulk. Glass fluid etches through the anti-reflection coating layer during contact firing. Because the paste is printed on ARC layer and the metal should make a contact with emitter, the ARC layer should be etched. Organics and solvents, on the other hand, are accounted for the rheology of the paste, like how viscous it is or its printability. For the backside, thin aluminum paste is used and screen printed on the backside. After the pastes are printed on both sides, the cells need to be fired at high temperatures up to 810 Celsius degree, 820 Celsius degree, so that metal makes a contact with emitter. This is a typical firing profile that is used in the manufacturing. Starting from room temperature, the cell enters the furnace, usually below 500 Celsius degree. The solvents and the organics in the paste will burn out. Around 650 Celsius degree, the aluminum powders will start to melt, and the top region is the firing time for front contact. During this short dwell time, the silver particles will be melted and sintered, and silver crystallites will grow into silicon to make a contact with emitter. Screen printed silver contacts has been the most utilized metal because of silver's excellent conductivity, solderability onto silicon. Its relatively low diffusion coefficient into silicon guarantees good contact with the substrate. Despite its great electrical advantages, Its cost corresponds to almost 40% of the total cost. This is proportional to width of the fingers because the wider the finger, the more the silver used. For example, in early 2000, the contact width was around 200 micrometer, and that corresponded to almost 350 milligram of silver per cell. As of today, with improvements in the screen printing and optimization of the pastes, the average width is 45 to 50 micron, which is around 100 milligram per cell. Considering that the purpose of PV market is to dominate the energy supply, the amount of silver adds up when the market grows. Recently reported by the Silver Institute that almost 9% of silver production goes to photovoltaic manufacturing. Keep in mind that today only 2 or 3% of electricity consumption is met by PV. What would happen if this number goes up to 20% or even 30%? Can silver as a precious metal keep up the production? And that's the big question. That's why we need the alternatives. If we are to use screen printing for the next 30 years, as ITR-PV reports predict, then these are the solutions we can come up with. Finer line printing to lower the amount of silver, which can translate to less than 15 micron contact width for 50 milligram per cell. Another option is to use some other metals instead of silver, such as nickel and copper. And there is one more option, that is optimization of the interface between silver contacts and silicon emitter, so the efficiency can be better and then the cost can be lower. So let's start with the first option that we have. For fine line printing, there are two options. We either need to make better paste or we need to optimize our screens that are used in the process. Typical screens look like this. When we zoom in the openings, you see the emulsion and the meshes underneath. To better see the structure, this is a clear picture. So those wires are there to give the strength that the screen needs when the squeegee pushes the paste through those openings. This mesh structure can affect the contact through the mesh count, angle, how many nuts in the opening of the screen. The effect is called mesh marks that increases the grid line resistance. The angle should be optimized so that there are less nuts in the openings. Tettner and his group from Fraunhofer have some findings that 35 degrees is the best because when the degree is right, there are minimum nuts and the mesh marks are kept minimum. To overcome this issue and optimize the screen, there are studies that are no nuts called nutless screens. Mesh wires are perpendicular to the opening and the nuts from the wire stays underneath the emulsion. The advantage of this design is obvious, that grid line resistance can be lowered and narrower grid lines can be printed. However, it still has some disadvantages, such as low throughput, since nutless screens cannot handle the shear pressure by the squeegee like a regular screen. The whole process needs to be slowed down. That's why these screens are not mainstream yet. ITR-PV predicts to go lower than 15 micrometer finger width by 2030, so this approach can be improved and adapted by that time. After fine line printing, our second option is utilizing alternative metals such as nickel and copper. To do so, there are some criteria that these metals should be accounted for. They should have a good conductivity, must be cheaper than silver, they need to work well with silicon substrates, and they should be durable. Most importantly, they should make an ambient contact with silicon. Nickel and copper are surely cheaper than silver, and they have good conductivity. So let's look at how they work with the silicon. After these are SEM images of a multi-layer printed contacts on a silicon solar cell. Since copper have an aggressive diffusion coefficient into silicon, and nickel has lower conductivity than silver and copper, they are generally used in two-layer structure. Here, silver as a seed layer at the bottom, and nickel or copper as a bulk layer at the top are printed on a cell. This can be done either with a two-step printing or printing the silver first and plating the bulk layer. Nevertheless, it is still using silver that increases the cost. It is also hard to print narrow grid lines with these methods. It is also reported that there might be some delamination between two metals, like you see in this picture, between silver and the bulk layer after the firing process, which fill factor suffers from high resistance, high grid line resistance. So what happens if we try to print nickel as a single layer contact? Printed nickel contact is not very common, but there are some studies, including mine, shows that it can serve the purpose if resistance problem can be overcome. Even though this contact you see here looks great in terms of aspect ratio, the high contact resistance suggests that nickel made a Schottky contact with silicon, and it is rendering the efficiency. Ideally, metals would form ohmic contacts if their work functions align with the conduction or valence bands of semiconductors. In practice, however, when a semiconductor forms a contact with a metal, a potential barrier called Schottky barrier emerges as a result of misalignment between the work function of the metal and electron affinity of the semiconductor. This graph shows the metal work functions for different metals. Considering silicon has 4.08 electron affinity, copper and nickel has higher metal work function. This will result in Schottky barrier height that causes the contact resistivity. This detrimental effect is caused by Fermi level pinning. Fermi level pinning arises from the surface stage of the semiconductor and happens for most used semiconductors such as silicon. The equation that governs the contact resistance, or the measure of the Schottky barrier height, is governed by this equation. Here, rho C being the specific contact resistance that we can measure and that depends on the doping concentration. That's where the selective emitter contacts come in. Increasing the doping concentration in this equation, we can decrease the specific contact resistivity and ultimately the contact resistance itself. So what it does is increasing the doping concentration underneath the contacts can help decreasing the contact resistivity and reduces the Shockley-Reed-Hall recombination. So that's why it can help the performance of a solar cell. There's also another way here to improve the performance of the cell, that is passivating contacts. Now this features a thin film between the contacts and silicon layer, usually silicon dioxide or hydrogenated amorphous silicon. This layer in between that you see here acts in a way that the semiconductor surface potential can be influenced by the overlying contact material, facilitating tunneling or thermionic emission through the contact structure. So about passivating contacts, there's another hypothesis that when a thick film paste is printed and fired, there will be a residual glass layer between the silver bulk and the silicon itself, and that will act as an insulator layer in between number one in this inset picture. However, to be able to obtain a continuous and uniform residual glass layer, material engineering needs to be addressed, such as sintering of the nanoparticles in the paste that I will not go into so much detail because it's a topic itself. But there's also an anti-hypothesis that the glass layer might include some semi-metal nanoparticles that you see in the scheme that can make this residual glass layer obsolete and acts as a transition layer for thermionic current flow. So it cannot be acting as a passivating layer when we talk about the energy band diagram. So another option to tackle this silver problem is to use 2D materials, such as graphene as a transparent contact. A new dry transfer method of graphene as transparent electrodes in textured silicon solar cell was recently reported by Yuan Zheng and his group in China. Even though it sounds great to have nothing on the front surface, considering graphene is transparent up to 95%, the technology is promising, but it needs to be developed. As you see, the current density is suffering due to the lack of carrier collection. So, as you see, there are many studies to challenge the issue silver usage brings to the table, but they are not mature as much as current technology, silver contacts, to be adopted by the industry. So I will conclude my presentation with these points. Using silver as an electrode for the fastest growing energy market is a problem, and that needs to be solved in the near future. There are promising ways in terms of reducing the silver usage per cell, but need to be matured by designing our screens better or by making better paste. And the third option and the last option is using the alternatives such as nickel, copper, and 2D materials, and they need to be improved. But before they are adopted, they need to be improved electrically, because we cannot afford to lose the performance of the cell in terms of cost saving. So I will conclude my presentation here. Thank you for your attention. And if you have any question, I'll be here to answer them.
Thank you, Veysel. So I don't know exactly how I can get question from the audience, but I don't want to go also in front of the schedule. So I think I will be here to ask you a couple of questions.
That's great.
One is, I'll ask from this perspective. So all these metals or the contacting scheme that you summarize is mostly for silicon, crystalline silicon contacting.
Yeah. Yes.
But you also at the end show that there are some materials where we can isolate metals. But can you also think about the question like amorphous silicon? So in the case of heterojunction solar cells. So what do you think from the direction, like putting, for example, a TCO or changing the metal, and what would be the consequence? Have you ever wondered about or work on the heterojunction technology?
Yeah, that's the good question. So the thing is, you know, I wanted to focus on the crystalline silicon solar cell because, like I showed you in the beginning, that it is like 95% of the market. So I just wanted to give you a solution that, you know, solves today's problem. But if you think about the amorphous silicon, then we're removing the high temperature firing. So that's why then copper and nickel or those kind of metals, they can be implemented in the processing flow. So that's going to make the silver obsolete. But the thing is, you know, they are not still in the, you know, big market share. So that's why it is not solving today's problems, but it has a very good future, like in next 20 years or so. That's what I'm thinking.
But I think one problem in this direction also is the temperature budget, right?
Yeah.
For when we consider these more exotic materials for isolating contacts or even amorphous silicon, so we have a temperature budget that we have to stay below that one. So do you see any correlation between the metals and the temperature budget associated with them? Or it just depends on the chemistry where they mix these colloidals?
I mean, there's a relationship between the two, but the thing is, you know, the solar cell as a whole requires some like passivation layer or some kind of thin layer to be able to improve the performance. So if you're not using ARC layer, then we're like doing the screen printing like less important. So that's why it is kind of important to look at the whole picture other than just, you know, crystalline silicon or amorphous silicon. But the thing is, like, if we remove firing from the printing process or the metallization process per se, then we open a lot of doors that we are stuck today. So
okay, so that is actually in the direction of putting a passivation, another material, not making metal directly contacting with the silicon, because every time when you put the metal in contact with silicon, you need firing for the activation of this interface.
yeah, because if there's an insulation layer between the metal and the silicon, then you're gonna have like an insulator rather than a silicon solar cell. So that's why it depends on the cross section of this metal layer or metal contact and the emitter actually. If you're getting rid of the passivation layer, then, you know, everything is possible.
Well, one direction also, once you put the metal in contact with silicon, that is a requirement for the electroplating, because in the electroplating, you need high electric field regions where the silicon metal can stick to. So what do you think about the future of electroplating itself? So do you have any prediction in terms of not only material cost or the process cost, but also for the scientifically how good contacts we can generate with this structure.
I mean, it has been tried out before, and they have very good results. I personally didn't work with electroplating or light-induced plating, but I mean, you can get as high performance as possible from electroplating or light-induced plating because you're targeting the seed layer and you're just doing your metallization in the chemical process. But the problem with the plating is the chemical waste, and it is hard to implement that processing flow into like currently manufacturing processes. So that's why it is kind of hard. And also like British Petrol, ITR, PV, they don't predict that plating is going to replace screen printing. They predict that something new is going to come up and then replace screen printing.
Along this direction, I think there's also a research on the inkjet printers, just putting directly the active layer. So what do you think about this one?
I actually work with the inkjet printing. The thing is, there was one Israeli company that they were trying to make an industrial level machine. They couldn't do it because you have to catch the screen printing high throughput. It is right now it's like 4,000 per cell an hour. So it is kind of hard because for inkjet printing, the nozzle system gets clogged all the time, and you have to make like a better paste, and you have to use nanoparticles for the ink, actually not the paste, but for the ink. So when you go into nanoparticles rather than micro size, then you're making like finer powder, which is increasing your cost again. But again, if you're talking about impact printing or non-impact printing, aerosol printing is the same actually. We're again talking about the high temperature firing as well. So I personally see that non-impact printing is going to emerge somehow, but not today actually.
Okay, so what you're saying is if you are going to eliminate this firing process, then you need to make this low contact resistance between metal and silicon, which is quite unlikely because I mean the work functions are known and the silicon is known, so everything is out there. So then you need to put a layer in between, which will reduce the contact resistance for you. And that is now the question is how can you deposit that layer cheaply, and what is that material is the open question from your perspective. Is that correct?
Yeah. So the thing is, what I'm thinking is like silver is being used by other electronic devices as well. Like when they're making like motherboards or some other electronic materials, they're using silvers as well. And the silver maturity, market maturity is so higher than the others. So if copper or nickel can reach to that level, it might be possible. But there's also the fact that, silver is the best if you think about the other materials like nickel and copper because of the metal work function. So I'm not so sure how we're going to pass the silver, because even though we can go as low as 15 micron per finger on the solar cell, it is still 50 milligram per cell. So it is a big number. So that's the big question.
Yeah, there's also after you collect the carriers, right? So silver has high conductivity, and relatively high resistance to the oxidation compared to copper, for example. It gives you a little bit of more time for maybe lamination, module fabrication.
There are some other studies like they are covering the silver nanoparticles with copper, like particle by particle, and then they are printing on the solar cells, but it is lowering the cost. But again, the oxidation of the copper, it just makes it hard to implement to the market.
Thank you, Veysel, for this nice presentation as well. So I think we can move on to the next speaker. Next speaker is Gamze Kökbudak from Middle East Technical University, Günam Center. Utilization of molybdenum oxide silver local real hole collecting contact in crystalline silicon PERC solar cells.
Thank you for the introduction, Dr. Yerci. My presentation is also pre-recorded, so I will be here.
Okay.
So. Good afternoon, ladies and gentlemen. My name is Gamze Kökbudak from Metallization. Today, my talk is utilization of molybdenum oxide, silver local rear hole collecting contact in crystalline silicon PERC solar cells. Unfortunately, direct metallization of crystalline silicon leads to highly recombinative interface, which limits the open circuit voltage of the devices. Here, common crystalline silicon solar cell structures, which are aluminum backsurface field solar cell and passivated emitter rear contact solar cell, are shown. PERC is an upgraded technology over the existing aluminum backsurface field solar cell. In order to improve open circuit voltage of the solar cells, there are three main ways to increase, which are heavily doping the crystalline silicon under the contact, reducing metallized region fraction, and using passivating contacts between crystalline silicon and metal. And since the formation of aluminum silicium region creates recombinative regions, it cannot supply sufficient passivation in aluminum backsurface field case. So PERC structure employs second way, reducing metallized region fraction by utilizing local aluminum backsurface field regions, but still there are local highly recombinative regions, which limits the passivation performance of solar cell. These local aluminum backsurface field regions in PERC structure also degrades the rear reflectivity. Recently, P-type solar cells utilizing only third way for VOC increase, featuring full area molybdenum oxide hole selector rear contacts, have been demonstrated with the efficiencies of 16.4 and 17.65%, as Dr. Nasser mentioned in the morning session today. And these direct metal molybdenum oxide contact structures are still limited by VOC and JST factors. So this study focuses on the latter two ways for VOC increase by applying partial molybdenum oxide hole contact at the rear of PERC structure. This substoichiometric molybdenum oxide's ability to form hole contacts is related to its large work function that promotes hole accumulation at these local regions created. One of the advantages of using molybdenum oxide instead of directly metallized contacts is low deposition temperature of molybdenum oxide and subsequent silver rear contacts. And this also preserves bulk lifetime together with low thermal budget. Another advantage is increased rear reflectivity, which enhances light encapsulation. The other advantage is low contact resistivity of molybdenum oxide P-type crystalline silicon contact with moderate passivation performance of molybdenum oxide layer. And only one work is reported until now where whole collected molybdenum oxide is utilized in PERC, achieving the efficiency over 20%. However, high quality, high bulk quality flow zone wafers were utilized on small area, 4 centimeters square, small area, and silver rear dot contacts, molybdenum oxide silver rear dot contacts are defined by photolithography, which are not compatible with the standard industrial cell processing. So in our design, standard industrial processing and industrial equipment are utilized to fabricate PERC with molybdenum oxide silver local rear contacts. We started with P-type Czochralski solar wafers with 180 micrometer thickness. Double-side texturing is performed to form pyramid texturing. Then emitter layer formed by phosphorus diffusion on both sides. A subsequent rear side doping removal is performed by single-side etching. Rear side is passivated by 5 nanometer aluminum oxide, followed by activation annealing and silicon nitride capping. And front side anti-reflective coating silicon nitride is also deposited by PECVD. Local contact openings were performed by picosecond laser at the rear side with approximately 7% of total area. Silver front contact formation is performed by screen printing, then rear side molybdenum oxide and following silver is deposited by thermal evaporation at room temperature. And you can see the SEM images of rear side micropyramids before and after laser processes. The use of industrial laser to create local contact openings likely damaged the silicon surface, so different molybdenum oxide thicknesses are considered. 7, 15, and 25 nanometer thick molybdenum oxides, as measured by spectroscopic absorptiometry on flat silicon wafers, are considered. The actual thickness deposited on the rear of PERC is assumed to be smaller, and poor surface coverage is expected on some regions of laser damaged pyramids or silicon surface due to the micropyramids, as seen in the SEM images. And 3 different molybdenum oxide thicknesses deposited by thermal evaporation are considered, and the relation between the thickness and the photovoltaic characteristic of PERC are investigated. But first, in order to find molybdenum oxide thickness and JSC correlation, heavy lighthouse is operated for optical ray tracing, and it assumes ideal cases at the interfaces and does not take into account electrical resistance losses, passivation losses, etc. And it assumes ideal emitter. And first, 5 nanometer aluminum oxide, and 120 nanometer silicon nitride silver stack is utilized. These are all full area, and JSC decreases when using aluminum instead of silver, mainly due to parasitic losses by aluminum in infrared region. And when molybdenum oxide directly contacted the silicon, JSC lowers, and introducing aluminum oxide silicon nitride stack improves JSC when 7 nanometer molybdenum oxide is used, and molybdenum oxide thickness increased to 15 nanometer. Increase of 15 nanometer reduces JSC due to parasitic absorption of molybdenum oxide itself, and no change in JSC with 30 nanometer thick molybdenum oxide is observed. And here you can see JV and EQ characteristics of the fabricated champion PERC from each molybdenum oxide thicknesses batch, and the area of the cells are 90 centimeters square. And PERC with 15 nanometer molybdenum oxide shows better EQ response in the infrared, as shown in the figure in the middle, indicating superior carrier collection in this region as compared to the 7 and 25 nanometer. And EQ response translates into improved overall JSC, as seen here in this graph. And 7 nanometer molybdenum oxide exposes part of silicon surface to silver, resulting in increased recombination, which leads to low VOC. 25 nanometer molybdenum oxide also imposes extra resistance losses, which causes high contact resistivity and low fill factor, and more parasitic absorption of light due to increased oxygen to ion concentration with increasing molybdenum oxide thickness, resulting in modest EQE response and lower JSC. Fill factor values show decreasing trend with increasing molybdenum oxide, as shown in the figure, which attributed to increase in the contact resistivity, which is measured by Oxide extract method. However, the average of fill factor of 7 nanometer thick molybdenum oxide is slightly lower than that of 15 nanometer, while the contact resistivity of 7 nanometer is smaller than contact resistivity of 15 nanometer. This suggests there exists local non-ohmic behavior imposing resistance losses arising from the direct contact between silver and P-type silicium through 7 nanometer molybdenum oxide. And this is in line with the low VOC reported from 7 nanometer molybdenum oxide. And 7 nanometer molybdenum oxide cannot fully cover the laser processed surface, resulting in defective local silver silicon zones with high recombination rates. And PERC soil cells with 15 and 25 nanometer thick molybdenum oxide exhibit identical VOC values of around 625 millivolts, suggesting better surface coverage for these thicknesses. While a clear correlation between molybdenum oxides and different aspects of molybdenum oxides, such as contact resistivity affecting fill factor and surface coverage affecting mainly VOC and parasitic absorption in the infrared affecting JSC, PV characteristics are observed. These parameters are shown to be strongly interrelated and dependent on molybdenum oxide thickness. In order to improve open circuit voltage of the PERC with molybdenum oxide solar cells, another cell was fabricated with additional passivation improvements. Starting wafers, texturing, diffusion, and single-side etching processes kept the same with previous studies, while 1 nanometer aluminum oxide is added under front-end reflective coating for better chemical passivation on the front side. The local contact opening was reduced to 3% from 7% in the set in order to compare the results with the optimized homogeneous emitter PERC structure we are fabricated by industrial tools. The other steps kept constant and only 1 molybdenum oxide thickness was used, which is 15 nanometers, since the highest efficiency results we have obtained when using 15 nanometer molybdenum oxide, as already mentioned. With the additional front-side passivation, VOC enhanced 11 millivolts, since 11 millivolts, while JSC is around the same values. However, the fill factor reduced drastically, while the fill factor of reference PERC is higher than PERC with molybdenum oxide structure. And all the variations indicates in the rear contact formation is problematic and needs to be analyzed and developed for further efficiency enhancement. But the area of the PERC with molybdenum oxide solar cell is much larger than the record efficient cells with a little efficiency loss. Still, further optimizations of front-side doping and silicon nitride passivation recipes is needed together with the contact formation analysis. And still, the VOC of the solar cells produced needs to be developed. For further improvements on VOC, symmetrical passivation structures were fabricated to mimic the rear side of homogeneous emitter PERC structure as shown. First, the aluminum oxide thickness is varied from 2 to 30 nanometer, applying two-step activation anneal in the case of all the produced solar cells up to now. And implied VOC results show that the maintained high passivation levels of 30 nanometer thick aluminum oxide is because the layers with these thicknesses can themselves provide hydrogen necessary to achieve chemical passivation of the silicon surface. And implied VOC improves after firing 2 nanometer aluminum oxide silicon nitride stack. And this improvement is because hydrogen diffusion from silicon nitride to the silicon aluminum oxide interface is more feasible through 2 nanometer layer, improving chemical passivation. On the other hand, the firing reduces the passivation quality of 5 nanometer aluminum oxide, since 5 nanometer may be thick to partially hinder hydrogen diffusion from silicon nitride to interface. Since still there might be potential for the various post-deposition and treatments to have different impacts depending on aluminum oxide thickness, especially regarding hydrogen diffusion. Different annealing treatments apply to 2 nanometer thick aluminum oxide film and aluminum oxide silicon nitride stacks. And for 2 nanometer aluminum oxide, forming as anneal at 425 degrees for 30 minutes seems more advantageous in terms of VOC, reaching implied VOC of 720 millivolts here. So for further PERC and PERC with molybdenum oxide studies, this stack with this annealing will be employed in order to reach higher cell VOC levels. To conclude, 90 centimeters square, 19.42% efficient PERC with rear local molybdenum oxide silver contact have been realized by industrial tools. Photovoltaic parameters are shown to be strongly interrelated and highly dependent on molybdenum oxide thickness. For VOC improvement, aluminum oxide thickness and activation annealing studies were performed and will be utilized in the upcoming studies. And fill factor improvement will be also addressed for the rear side of large area PERC with molybdenum oxide structure. Thank you for listening. If you have any questions, I'll be glad to answer.
Thank you, Gamze, for this very nice presentation on utilization of molybdenum oxide in the PERC solar cells. I will have one question at least. So as you, I think, realize that replacing a material or adding a material into the process is quite a suffer and engineering process, not only thickness, but also the firing process. So can you tell a little bit on the, like, have you done any changes in the firing process or is the standard firing process? Can you mention about the firing as well?
Yes, thank you for this question. For the firing, actually, the optimizations were done on the standard PERC structures first, and then molybdenum oxide deposition and the subsequent firing. But this firing is for front surface, since for the back side, we are not doing firing process after deposition. So we did the optimizations only for the front surface of the PERC structure, then applied to molybdenum oxide PERC structure. So firing optimizations were done, but only on the standard.
Okay. But that firing also, the temperature profile of the firing, or let's say the temperature profile that molybdenum oxide undergo, can also affect the performance. Is that the condition? Or you don't see any difference in the molybdenum oxide performance when you change the firing temperature in the front side, or you haven't changed it yet?
Actually, after molybdenum oxide deposition and subsequent silver deposition, we are not performing.
There's not, so it's already done in the previous one. Okay.
It's not effective.
Okay, I got your point. So what is your projection on replacing molybdenum oxide if needed? So do you think there are other materials which are more suitable than molybdenum oxide for to use in the PERC side, or there's no?
Actually, we have started to work with vanadium oxide also and with the tungsten oxide, but we couldn't yet achieve the solar cell production with these, but only some characterizations were done, TM images and etc. Were taken, but we are planning to continue with these the layers also.
Okay. Do you also see any prospect on P-type layers like nickel oxide? Because the ones that you mentioned, I think they're all, vanadium oxide is P-type as well.
Yes, yes.
But do you have any selectivity from that perspective when you're choosing the material?
Actually, molybdenum oxide was the starting point. With tungsten oxide, we have achieved the solar cell actually with about 18%.
That's also an N-type material, right?
Mm-hmm. Yes, but we have some plans with other hole and electron selective layers also. We are planning to use also electron selective layers from the front side. So this molybdenum oxide was just a starting point, but we are planning to do other materials also.
Have you have a chance to do a relatively longer term stability studies of molybdenum oxide, like keep it in the shelf for a month or for 2 months? Have you ever remeasured the cells?
Actually, not yet. Just I have measured 1 week after first measurements, and the result was quite similar, but not 1 month. I can try and see.
Okay, I think you should keep an eye on stability, right? That's actually one of the things about those relatively unknown materials, like what is the like diffusion of metals through these materials is quite unknown, and they're very thin. So you may end up with a couple of months or so, maybe you may end up with some metal accumulation at the interfaces, which is not known. And also the oxygen, these materials, they don't like oxygen that much. So their stability or their stoichiometry require more oxygen, but they are working with the non-stoichiometric conditions. So that means they like to get rid of oxygen in time. So silicon might be a material which is accepting oxygen that may change the interface dynamics. So I think it's something that should be addressed in later talks. Hopefully, we will hear from you. Okay.
Thank you.
Thank you, Guy. I think we can move on to the next speaker. So Haris Mahmoud, are you there?
Yes, sir. I'm here.
How are you?
Yeah.
Good to see you, at least on the computer. I've seen you once.
Yeah, but it seems that the host has stopped it. Start my video.
Okay. So let me start introduce you and then start your presentation. So Haris Mahmoud is from Information Technology University of the Punjab in Pakistan. And his talk titled as Physical Device Simulation of Dopant-Free Asymmetric Silicon Heterojunction Solder Cell featuring tungsten oxide and ultra-thin silicon oxide as a whole selective and passivation stack layer. And we can start the presentation.
Ladies and gentlemen, Assalamu alaikum. My name is Haris Mahmood and I'm working as a faculty member at Information Technology University Lahore from Pakistan. And I would like to thank the organizer of a photovoltaic conference at MITU Turkey for inviting me to present my research topic. So let me share my research presentation with you. So the title of my research presentation is a physical device simulation of dopant-free asymmetric silicon hydrostructure solar cell featuring tungsten oxide as a whole selective layer and ultra-thin silicon oxide integrated for passivation. So along with me, there are other co-authors from Nust University, ITU, as well as from MITU Turkey. So here are the outlines of my research presentation. So starting with the introduction to my research work, the literature advertises that the highest efficient silicon solar cell has a conversion efficiency of 26.6%. That is based on the structure of interdigitated bad contact silicon heterojunction solar cell structure, IBC SHJ structure. So in this type of solar cell, the both sides of the silicon wafer is passivated with amorphous silicon, and the top side is capped with the n-type amorphous silicon layer, and the bottom side is capped with the n-type amorphous silicon and p-type amorphous silicon in a pattern fashion. So this means that the front surface of the sunlight of this device is receiving the full coverage of the sunlight. So this type of solar cell has a higher short circuit current density of more than 40 milliampere per centimeter scale. So however, there are various challenges associated with state-of-the-art device such that it is expensive to produce commercially such type of device because of the complex lithography requirement issues, as well as there are challenges associated with the dope amorphous silicon layer, such as because of the low band gap of amorphous silicon, it tends to induce unnecessary parasitic absorption within the device. Similarly, there are Gaussian and tail defects present within the film that contributes to the increase in recombination centers. And of course, the temperature-intensive fabrication process would be required to fabricate the amorphous silicon layer. So for any solar cell device, the band diagram is a very important figure to determine the charge transportation characteristics of the device. So for a traditional H heterojunction with intrinsic thin film solar cell HIT device, the energy band diagram tells us that the energy barrier height is approximately 1.2 electron volt against the minority carrier electrons at the front interface. Similarly, the energy barrier height is approximately around 0.4 electron volt against the majority carrier holes. So these kind of band offsets promote the charge transportation of specific charge carriers. For example, 1.2 electron volt at the top side, a conduction band offset will try to repel the minority carrier's electron away from the anodal interface. And the low barrier at the anode side for the holes will promote the transportation of the majority charge carriers towards the anode contact. However, there are challenges associated with this type of device, such that it might happen that because of the some of the high energetic carriers, electrons may jump this p-type amorphous silicon barrier and may recombine with the host, thereby increasing the recombination of the device, and ultimately leading to the reduction in the photovoltaic performance. So we propose the dopant-free layer, the solar cell with the dopant-free layer. So the purpose is to alleviate the dopant-related concerns as well as to improve the band offsets of the passivated layer for improving the charge transportation characteristics. So such type of solar cell is known as dopant-free asymmetric silicon hydrostructure solar cell. So in which we typically in such dash solar cell, we try to replace the dope amorphous silicon layers with the respective carrier selective filament. The whole selective layer will be replaced with a molybdenum oxide or some other high work function material, and the N-type amorphous silicon layer will be replaced with some low work function material of transition metal oxide. So we propose the tungsten oxide as a whole selective layer for our structure, and the titanium dioxide for our electron selective film layer and the structure. So the basic purpose of the implementing tungsten oxide is that it tends to replace the p-type amorphous silicon because of its high work function of around 7 electron volt. So the advantage of employing high work function is that it induces the formation, induces the inversion of the crystalline silicon surface on the both sides. Similarly, the higher band gap of 3 electron volt will reduce the parasitic absorption, and the electron selective film of titanium dioxide will be having a low work function. So we will simulate this work will explain the simulation results of the solar cell structure that employed with tungsten oxide at the front and titanium dioxide at the rear. And then we have also implemented a passivated oxide in order to check the effectiveness of the silicon dioxide layer as a passivation layer. So simulation and mathematical model, Silvaco-Tikar model was used, Silvaco-Tikar simulator, and several parameters were varied at AN 1.5 spectrum at a temperature of 300 Kelvin. So we have analyzed various parameters by changing the work function of tungsten oxide as well as the influence of the electron affinity of titanium dioxide on the photovoltaic performance. And in the end, we have checked the effectiveness of the silicon dioxide layer as a passivation layer for our proposed device. So the novelty of this structure is that such type of solar cell structure has never been simulated before. Particularly the DASH device employing the passivated silicon dioxide has never been simulated in the literature before, nor it has been fabricated in the literature. So several mathematical models were employed, such as charge carrier transportation, Auger recombination, concentration dependent SRH, band gap narrowing effects, as well as Fowler-Northam's approximation for tunneling across the silicon dioxide region. Similarly, several assumptions were also taken for the simulation. Shown is the table in which we have used various input parameters, simulation parameters for tungsten oxide, silicon dioxide, and titanium dioxide. And the assumptions we have taken that the interface recombination velocity was specified, as well as the defects density layer between the tungsten oxide and the silicon dioxide, as well as titanium dioxide and the silicon dioxide layer was also incorporated in the simulation. Now we come to the results and discussion. As a result of implementing the high work function material with the crystalline silicon, what happened is that it induces the band bending. A significant amount of band bending happens at the crystalline silicon and the molybdenum oxide interface. So molybdenum oxide is also a transition metal oxide layer. It is also a Hurst selective layer with a high work function of around 6.9 electron volt, which is similar to the work function of a tungsten oxide. So as a result of this interface inversion, significant band bending takes place, and the hose will be transported via tunneling or by like a transportation across the defect stage towards the anode contact. Similarly, the higher potential barrier will be created against the minority electrons, and the electrons will be repelled away towards the cathode contact. So such type of energy band diagram has been taken at the thermal equilibrium. Now the effect of a tungsten dioxide work function on the band bending. So we can see that if upon increasing the work function of tungsten dioxide, the energy barrier against the minority electron is increasing at the top anodal interface. So if we decrease the work function of tungsten dioxide as shown in the blue color, as we can see for the conduction band, this is shown on the right side is the conduction band figure, on the right, on the left side is the valence band figure. So with part A, upon increasing the work function of the tungsten dioxide, the band barrier increases against the minority electron, and similarly, the band barrier against the holes will decrease. So if the band barrier against the hole decreases and the band barrier against the electron increases, so that means that the electron will be repelled away and holes will be easily transported across the tungsten dioxide layer towards the ITO interface. Electric field is also affected as a result of a tungsten dioxide work function. We can see that the electric field decreases with the low work function values of tungsten dioxide. So this is because we have seen in the previous slide that at the low work function values of tungsten dioxide, insufficient band bending would warrant the low bending band offsets that will ultimately lower the electric field. Similarly, we have also studied the effects of the interfacial defects on the photovoltaic performance of the device, and we have seen that the S-shaped behavior was observed at a higher interfacial defects values. And this high DIT values can be approximated by the unoptimized deposition conditions as well as the increase in oxygen vacancies. So with the increase in the oxygen vacancies, the Fermi level of the tungsten dioxide will be pushed towards the conduction band, and that will lead to the decrease in its work function values. So by decreasing the oxygen vacancies, the Fermi level will be pulled away from the conduction band minimum, so the work function value will increase. So it is very, very important to reduce the interfacial defects by strict exposure control. Similarly, we have also studied the influence of the titanium dioxide electron affinity on the photo band bending. And it can be seen that in the part A, the part A shows that at low electron affinity of 3 electron volt, the electrons coming towards the cathode will be easily, you can say like a thermonic emission will be happening. So it will be easily transported towards the cathode contact. But if we increase the titanium dioxide electron affinity to 4.6 electron volt as shown in figure B, then there will be some sort of band bending happenings near the cathode interface as well. So this increase in the electron affinity of the titanium dioxide will try to trap the electron at the cathode interface, thereby leading to the recombination with the host, hence decrease in the photovoltaic performance would be observed. So the comparison of the energy band diagram with the Graphine structure and our proposed structure shows that with the intrinsic amorphous silicon passivated amorphous silicon layer, the electron barrier height of around 3 electron volts has been observed. Whereas if we incorporated silicon dioxide layer as a passivation layer, then the electron barrier height would be further improved to around 6 electron volt. So this means that even the highly energetic electrons will have difficulty in hovering over the silicon dioxide layer to be collected at the anode contact. So it is expected that photovoltaic performance will be enhanced in the case of the silicon dioxide, as it will be confirmed in the coming slide. So by inserting the silicon dioxide layer, we have been able to maintain the electric field within the oxide layer as shown in the figure. And that electric field will try to accelerate the holes towards its layer, because of it's like a tunneling process across the silicon dioxide layer, and it will be then ultimately collected at the anode terminals. So the high electric field has been maintained with a large Flex function of tungsten dioxide. And the thickness of the silicon dioxide also influences the carrier tunneling and the photovoltaic characteristics of the proposed device. And we have seen that the optimized thickness of 1 nanometer of a passivated silicon dioxide would warrant the efficiency, conversion efficiency of around 24%. Finally, I will discuss the comparison of the reference device with our proposed device. And the reference device that was fabricated has the efficiency of 20.79%. And the same structure was simulated with the same set of parameters as was employed in our work. And it showed the conversion efficiency of 20.88% for the reference device. So our proposed device has a better open circuit voltage because of the large work function of tungsten dioxide equal to 751 milliwatt, and the better current density, better fill factor, and better conversion efficiency of 24.06%. So conclusion, that solar cell structure based on tungsten dioxide and titanium dioxide as hole and electron selective contacts has been simulated with Silvaco TCAD, and the higher work function of tungsten dioxide assists in lowering the energy barrier for holes, thereby improving the photovoltaic performance, and the reduced interfacial defects assist in increasing the photovoltaic performance, and the low electron affinity has to be used for the titanium dioxide. Smaller oxide thickness promotes the enhanced tunneling of the charge carriers, and the optimized thickness of 1 nanometer has been simulated to be taken as an optimized thickness for this proposed dash device solar cell. Thank you very much.
Thank you, Haris, for this nice simulation study that you have just showed. I'll have one question. So your simulation can be as good as your assumptions at this point. So I will ask you a question about your assumptions at the contacts. So you use tunneling, I think Fowler Northam you said, right?
Yes,
tunneling mechanisms used. So how accurate do you think those mechanisms, and how can we make this simulation superior? Like what could be experimental and simulation methods can be merged together so that we can get more accurate simulations at those interfaces?
So first of all, we need to take the parameters. The simulation parameters should be such that they should be derived from the experimental values. So in this case, we have used the experimental data such as the refractive index data, the optical dispersion data, as well as the band gap of the tungsten oxide, as well as the molybdenum, tungsten oxide work function. So all these parameters have been taken from the experimentally derived experiments, and those data have been then incorporated into the simulation studies, and then we have performed this simulation on the Silvaco TCAD. So as I have seen, as I have shown on the last slide, there was a comparison of the reference structure with our work. So that reference structure, the data for the amorphous silicon, the data for the crystalline silicon, as well as the data for p-type amorphous silicon, n-type amorphous silicon, they all were taken from the experimentally derived data. So we have incorporated those experimentally derived data, and then we have further optimized it. So that optimization can be performed in the form of like optimizing the like a light reflection. For example, if we have assumed that the experiments, they have assumed that 10%, I have further optimized it to like 5%. So 5% means that we are further reducing the reflection of the light from the top surface. So if we increase it, if we somehow manage to incorporate these kind of simulated parameters in our actual simulation studies, in our actual experimental studies, then we can expect our device performance to be achieving at least the efficiency comparable to this simulated one. So it is like this structure is the optimized structure, the 24% of the tungsten oxide based structure, that is the optimized structure. But somehow it may happen that during the experimental stage, we may not be able to achieve 24%. So it is very, very important that we should be able to achieve this work function of 7 electron volt, as well as we should also reduce the interfacial defects at the interface between tungsten oxide and crystalline silicon to less than 10 raised to power 12, then we can expect our device performance to be performing up to 24%. Otherwise, if we take that real experimental data, then maybe it can be less than 24% as well. But this one is the optimized structure, so this is what I have to present for this one.
Okay, thank you, Aris. I think I have to stop at this point because of time limitation. I will move to the next speaker.
Okay, thank you.
Erkan, I hope you're there.
I am here, but Serkan is not able to for today. I am Ali Altuntepe. He is my colleague, and I presented our study, and also I will try to all the questions.
Whose video recording will see, Serkan or yours?
Actually, me recorded this video.
You recorded for his video.
But Serkan, I guess, writing in your computer. I don't know.
Okay, I think I understood the situation. So Serkan will make the presentation from Niğde Ömer Halis Demir University in Turkey. And the title will be The Fabrication of Silicon Solar Cells with Graphine and Molybdenum Doped Zinc Oxide. So let's see the video.
I would like to say hello to everyone. My colleague Serkan is not able to present our study. I am Ali Altuntepe, and I will present the fabrication of silicon-based solar cell with graphene and molybdenum doped zinc oxide. Firstly, when we check outline, I will talk about graphene, fabrication process of graphene, and characterization. Then we will talk about molybdenum doped zinc oxide and molybdenum doped zinc oxide graphene hybrid structure. After that, we will discuss fabrication process and characterization. Then MZO and hybrid solar cell structure, fabrication process and characterization. We will talk about this issue. Finally, I will tell something about generally. Firstly, what is the graphene? Actually, we know this material. When we write something with pencil, we leave many graphene layers on the paper. Just I'm telling for your imagination. 1 millimeter graphite consists of 3 million graphene films. It means that we are talking about so thinnest material. On the other hand, graphene is basic building block of other form of carbon fullerene. And graphene has most of remarkable properties, such as 98% optical transmissions, high mobility, high thermal conductivity. In addition, when we check other properties of graphene, graphene transparent than the glass, stronger than the steel, flexible than the rubber, lighter than the paper, conductive than the silver. These remarkable properties make it available for large-scale application area, especially solar cells. Indium tin oxide is one of the available TCO, which is also commonly used. However, ITO has some disadvantages, such as limited resources and ITO is brittle. For this reason, we investigating other type of TCOs, for example, doped zinc oxide. And in this presentation, I will talk about molybdenum doped zinc oxide, I mean MZO. In fact, I will provide some solar cell results with MZO and hybrid TCO, which consist of MZO and graphene. There are a few methods for graphene synthesis. Chemical vapor deposition method, CVD, one of the most popular methods because of large-scale and homogeneous graphene synthesis. The growth mechanism in CVD based on the composition of hydrocarbon gases at elevated temperature and the diffusion of carbon atoms onto the metal surface. Many parameters is so important for the graphene synthesis: substrate, flow rates, and temperature. Even your gas purity can be affect your graphene quality seriously. So most of parameters should be optimized for the large-scale graphene synthesizing. We used polycrystal copper as substrate. 30 minutes growth time was applied at 1000 Celsius degree for single layer graphene synthesis. On the other hand, graphene layer should be transparent for solar cell application for the transfer. We are using wet transfer technique, which is called polymer supported transfer. The polymer we use it is PMMA. To begin, copper was coated with PMMA in spin coating. Then copper baked on the hot plate for a few minutes. After that, we clean off our copper backside in the plasma cleaner. Then we get off our copper with etchant in the iron chloride. In this figure, PMMA and graphene floating on the iron chloride etchant. Then we can transfer our graphene any substrate. On the other hand, characterization is other important for the graphene, especially Raman characterization. Graphene has two main peaks, which are called G and 2D. G peak represents crystallinity of the graphene. 2D peak can be called track peak of the graphene layers. In addition, graphene has another peak called D. D typify the fact on the graphene structure. G and 2D come with this peak. And we can determine our graphene layers with the spectra. And the spectra show us the multi-layer graphene. Zinc oxide can be enhanced by doping electrical and optical properties. And zinc oxide can be improved by molybdenum doping. Molybdenum atomic value is close to zinc oxide, and also molybdenum atomic value is 0.042 nanometer and zinc atomic value 0.074 nanometer. So molybdenum doping is easier for zinc. Molybdenum getting zinc oxide structure. There are a few methods in order to fabricate MZO films, such as PVD, CVD, sol gel. MZO films were fabricated using sputtering technique in PVD. 10 different set of samples with different thickness. We fabricated MZO films from 50 nanometers to 500 nanometers. The reason we have investigated such a large scale is to find out the best film thickness in terms of optoelectronic properties. By the way, we didn't apply any pre or post annealing to fabricated MZO films. When we check the MZO films optical and electrical properties, when we increase of the MZO films thickness, sheet resistance decrease. On the other hand, with increase of MZO film's thickness, optical transmission was affected seriously. Generally, MZO films optical transmissions 75%. This result can be related with MZO crystalline structure because we observed the same result with aluminum doped zinc oxide, gallium doped zinc oxide. And on the other hand, we can know from literature and when we increase of the film thickness, at the same time we enhance of the crystallinity. So sheet resistance of MZO can be decreased with increasing film thickness, and optical transmissions weren't affected seriously. When we consider electrical and optical properties of MZO 150 nanometer films can be best candidate for the fabrication of solar cells. This situation could be related also, on the other hand, MZO graphene hybrid structure and sheet resistance increased after that. This situation could be related with high sheet resistance of graphene. Considering of only sheet resistance is not enough to determine hybrid structure properties because of graphene has high mobility, high work function. So it can overcome handicaps on the hybrid structure. In this figure, when we check the 150 nanometer SEM match of MZO, in addition, we can see X as the pattern for 150 nanometers AZO film, and crystalline size is about 58 nanometers, and also we check the other values in this table. 1-inch MZO and hybrid solar cell fabricated, then cell efficiency was measured by solar simulator. So that MZO and hybrid solar cell efficiency were compared with each other. At this point, when we investigate MZO and hybrid solar cell efficiency, MZO solar cell has 12% efficiency, and hybrid solar cell has 50.5% efficiency. Solar cell efficiency was increased by graphene. Most of parameters are reported for solar cell efficiency, such as fill factor and open circuit voltage. Fill factor was decreased in the MZO graphene hybrid structure. This situation related with graphene has high sheet resistance because high sheet resistance can be limited fill factor. However, there isn't serious decrease in fill factor. On the other hand, VOC was increasing with MZO graphene hybrid structure because graphene has more work function than MZO. MZO work function is approximately 4.1 electron, and the graphene work function is 4.5 electron. So we increase of our solar cell efficiency with graphene and MZO hybrid structure. It means that MZO and graphene can be used as transparent conductive electrode for the solar cell, especially silicium-based solar cell structure. Large-scale, single-layer pristine graphene was synthesized. Molybdenum doped zinc oxide films were fabricated using PVD. Hybrid TCE structure was fabricated by transferring graphene onto MZO films. Silicon-based solar cell with MZO and MZO graphene TCE were fabricated and measured in terms of efficiency. Thank you for your attention. Any questions?
Thank you, Ali. I have a question. So the question about your VOC and fill factor. So the correlation between the VOC and fill factor, fill factor looks much higher than it's supposed to be when you compare with the VOC. And the one question, the other one is when you put the graphene, how come your VOC changes? Because graphene is touching to molybdenum oxide, so that shouldn't affect the recombinations. Can you comment on this too?
Yeah. Actually, firstly, we know from literature and also previously our study, and when we consist of the graphene and other TCO structure and also ITO and other gallium doped zinc oxide, molybdenum doped zinc oxide, at the same time we can limit it off the sheet resistance, because graphene has high sheet resistance. So at the same time we decrease of the fill factor. And also, when we check with other TCOs, such as I2, especially I2 and graphene is studied in the literature. And when we consist of the ITO and graphene, also MZO and graphene structure, at the same time, we can increase of the VOC. And this situation related with the also high work function of the graphene. And also, yes, some recombination can be occur of this structure. And also, this recombination limited of our efficiency at the same time. And we set off most of solar cell at the same time, also one solar cell, but we measured of the maybe 100 solar cell efficiency, and we compared each other, because graphene transfer also can be consist of the handicaps for the solar cell fabrication. On the other hand, graphene and also can be ringless, all other things can be occur of our solar cell, but all TCOs, I'm talking about for all TCOs, when we consist of at the same time, we increase of the solar cell efficiency. And this situation, and as I told you, related with from literature and also our some experience, and with the high work function of the graphene and also high mobility of the graphene. And then when we compare with the other MZOs and mobility of the TCOs, and graphene can be best candidate for the applications.
Ali, I will have one more question. So have you measured the series resistance, sheet resistance, contact resistance, and the surface recombination velocity of your devices? Actually,
we measured of the some series resistance for our working, and also of course at the same time lifetime, when we compare of the lifetime, and we increase of the lifetime with the graphene actually, because of the some high maybe can be related with the transmission of the graphene and also mobility of the graphene, and charge carrier of the graphene can be related with this situation. But on the other hand, as I told you, we cutting manually our solar cell, and also at the same time some problems or some handicaps can occur at the same time. So we fabricated of the 100 cells for the measure of the solar cell efficiency, and we compared each other. So we decided to increase of the solar cell efficiency with this method, and other working can also continue.
All right, thank you, Ali. I think let's conclude our session number 3. So we'll have one more session, I guess, at least. Let me check the time. It's supposed to be here, just 1 second. Yeah, here we go. So the next section will start at 4:30. So that's about like 20 minutes from now. Okay, thank you all the speakers of this session.